before we get started with Chapter 13 review, this is a reminder. Today is April 8th, 2025. Our normally scheduled class next time is April 10th. I won't be here. Fortunately, there's a buffer day built in, so we're going to get the review done today for exam 7. And Thursday, then, the 10th, will be a free day. So let's get started with our review of Chapter 13 material on gases. All right, I'm going to look at number 1. There are 2 balloons. Both have the same size, same temperature. So we got a balloon here, and we got a balloon there. It's supposed to be the same size. So that means the volume of this one equals the volume of the second one. And the temperatures are also the same. Okay. One balloon contains hydrogen. Well, let's make this one hydrogen. And the other balloon contains carbon dioxide. Okay. The hydrogen balloon floats and the carbon dioxide balloon sinks in air. Okay. So this one floats in air. This one sinks in air. What else are we given? Which one contains the greatest number of molecules? So we're saying, what's the relationship here with the number of molecules? Well, what else? What other factor are we not given? Well, let's see. If we know the pressure, the volume, temperature, and moles, then we can describe the physical behavior of any gas. So we're given temperature, they're equal. We're given volume, they're equal. How about pressure? This is an assumption that since these balloons are together in this description, in this thought problem, they should be the same pressure. If that's the case, then Avogadro says that they have the same number of moles. So those should be equal. Okay. What can we say? Well, that answers the question. Which balloon contains greater number of molecules? Neither one. They both have the same number of molecules. Both balloons contain the same number of molecules. Okay, why does this one float and that one sink? It's all based on density. So the density of this one has to be greater than the density of air. And this one has to be less than the density of air. Right? So how do you get there? Well, remember what density is. Density equals mass divided by volume. Since the volume is the same, we'll just leave that one as is. So, what's the difference between the two? If the volume is the same, the mass of the CO2 must be greater than the mass of hydrogen. So what's the ratio? I know this is not part of the problem, but what's the ratio between the two masses? Well, if you got the same number of molecules in each one, then the difference in mass between the two is proportional to the mass of the individual molecules. So this one is 2.02 grams per mole. And this one is, let's see, 12.01 and 32.04, 44.01 grams per mole. Okay. So This balloon is 22 times heavier than that one. That's where the density difference comes from, is the difference in mass. All right. See if this works any better. Not much. It just smears it. All right. Number 2. You place 15 grams of nitrogen gas and 15 grams of hydrogen gas in a container fitted with a massless, frictionless piston. Okay, let's draw a picture. So there's our container. And let's see, let's put our piston about right here in the middle. Okay. So there's our piston. And we put 15 grams of hydrogen. And 15 grams of nitrogen in that container. The original volume of the container is 11.4 liters. So this is 11.4 liters. What's the volume after the reaction has run to completion? Okay, so if this is the reaction, two there, and 3 here. Assume constant temperature. Okay, and we should also assume constant pressure, right? Pressure is not going to change. So what are we dealing with here? We're dealing with a reaction that produces fewer moles of gas after the reaction than before. All right. So the absolute amounts here, they really don't matter. We're talking about a ratio. So what ratio are we talking about? We're talking about moles and volume. That's Avogadro's law. So we know that the volume, initial volume and initial moles equals final volume and the final moles. Right? So let's get our information up here. The ratio between the two reactions is the number of moles is in the coefficients. So here we have 4 moles of gas. And here we only have 2 moles of gas. Right? So the ratio of these two, let's rearrange the equation. Let's say initial here, put that over here. This comes over here, like that. Okay? So what's the ratio here? Well, this is initial is 4, and final is 2. So that's equal to a ratio of 2. All right, so if the initial volume is 11.4 liters, what's the final volume? The final volume then is equal to 11.4 liters divided by 2. Let's see if I can do that in my head. So it should be 5.7 liters is the wrong answer. Oh. Okay. Leave that there. Well, we can't leave that there because I need the room. This would be the stoichiometric answer. But since we're given absolute amounts of nitrogen and hydrogen, one of them is going to be limiting. All right, so let's back up and solve this problem correctly. All right, we got 15 grams here and 15 grams here. Then we need to convert this to moles. Okay. So grams on the bottom, moles on the top, and this should be 28.02. Right? Need a calculator. So this is 0.535 moles of nitrogen gas. And this one would be converted 1 mole, 2.02. Okay. Which is 7.43 moles of hydrogen. Okay. What's the ratio here? Ratio is 1 to 3. So we need 3 of these, 3 moles of these for every one of those. What's 3 times 0.535? Well, it's about 1.6, right? Approximately 1.6 moles of hydrogen required. We got plenty of hydrogen. This is excess. This is limiting. Okay, now we can go to our solution. We had VI over VF equals NI over NF. Actually, we're not finished yet. So here, we have to do exact calculations here. Let's see. Let's go back here, times 3. This is 1.606 moles of hydrogen used. So how much hydrogen remains? 7.343 minus 1.606. And I get 5.82 moles of hydrogen remain. Okay. That's how much hydrogen is left over. All the nitrogen is used. So how much ammonia is produced? Well, if we start off with this much nitrogen, 1 to 2, we're going to have twice as much. .07 moles produced. Okay. So what we're saying is, how many moles of gas did we start with? The initial moles. Right? N sub I would be 0.535 nitrogen plus 7.43 hydrogen. Okay. How about the final? There's none of this left. What we have left here, we have uh, 5.82 moles of hydrogen remain, plus what we produced over here, 1.07. Okay. And the initial volume is 11.4 liters. Okay. Now we can solve our equation for the actual volume. So VF is going to be 11.4 times 5.82 plus 1.07 divided by 0.5 8.35 plus 7.43. Okay, so 5.82 plus 1.07 is 6.89 times 11.4, and that's 78.55 divided by 0.535, enter, 7.43 plus, and this is 7.965. So divide that into that, get 9.86 liters. There. Nearest one we've got in our answers is 9.87, rounding errors. Okay, so this problem was more complicated than I initially thought. I first treated it as a stoichiometric problem, but it's not. It's a limiting reactant problem. So we had to find out how much did we start with, how much did we end with. Then we could invoke Avogadro's law. Okay, number 7. All right, you're holding 4 balloons. Each contains 6 grams of a different gas. 4 balloons with 6 grams. All right, so the sizes we don't know. The balloon containing which gas is the largest? All right, if they have the same mass, they have 6 grams of gas in each one. Okay. And let's say we have nitrogen, helium, krypton, and neon. All right. Which one's going to be the largest? Well, obviously, if all conditions are the same, temperature, pressure, then the volume is going to be related to the number of moles. We've got grams. So how do you know moles? Well, molar mass, of course. And so what's the molar mass of nitrogen? Well, let's see, it's 28.02 grams per mole. Helium is about 4 grams per mole. Yeah. Krypton is 83.80. And neon is 20.18. 20.18 grams per mole. Okay. If they all have the same mass, then how do they get that mass? Well, if each individual atom or molecule weighs a certain amount, the one that weighs the least amount will require more moles, more particles to make that mass. So the one that has the most particles will be the one with the smallest molar mass, which is this one. Helium. Okay. Which one would be the smallest volume? Krypton. All right. Okay. Number 8. Hydrogen peroxide decomposes to form water and oxygen according to the following equation. Hydrogen peroxide, let's see, aqueous, decomposes to form water and oxygen gas. Excuse me. Suppose 145.9 grams of hydrogen peroxide. Okay. Decomposes and all the oxygen gas is collected in the balloon at 1 atmosphere and 25 degrees. So we're going to get a certain number of moles of oxygen here, and it's collected in a balloon at 1 atmosphere and 25 degrees C. What's the volume of the balloon? Well, let's work this one backwards. If we want to know the volume, what type of relationship do we have here? Well, we've got volume, temperature, pressure, and moles to consider if we want to characterize the gas in its physical state. So what relationship, is there a formula that relates all of these items? Yes, there is. Right? The ideal gas equation. Well, we want to know volume. We know pressure. We can calculate Kelvin temperature. R is a constant. What we need is moles. So how do we do moles? We have to use stoichiometry of the equation. So we have to convert this one into moles. Otherwise, we can't move that direction. All right, so hydrogen peroxide is what? All right, 2 times 1.01 for hydrogen and 2 times 16, right, for oxygen. (34.02 grams per mole). So 34.02, go. And we divide that into 145.9, and I get 4.289 moles of hydrogen peroxide. Okay. Now we want to convert that to moles of oxygen. So what's the ratio here? What's the conversion factor? Well, we want hydrogen peroxide on the bottom and oxygen on the top. That's 1 and that's 2. So we divide that value by 2, and we get 2.144 moles of oxygen. Now we can solve our equation. 2.144 moles, 0.08206 liter atmosphere per mole. Okay. Temperature, 25 plus 273. Right? And pressure is 1 atmosphere. So K's cancel, atmospheres cancel, moles cancel, and leave us with liters. So the rest is crunching numbers. 0.08206. And 25 plus 273 is 298 times. So what do we have here? Volume is 52.4 liters. Okay. That's how it's done. Number 11. Now, if you're not trying to work any of these types of problems on your own, this is just a review. If you're not working any of those problems in the review document or in the practice Brightspace quizzes, then everything I'm doing today is just going to look and sound like ancient Greek, right? You're going to be completely lost. So I encourage you to try to work as many of these problems as you can. Number 11. A gas is collected over water at a certain temperature. Total pressure is 758 torr. All right, so we're collecting a gas over water. Got water here. And we've got let's say a graduated cylinder. And the pressure is 758 torr. Right? The vapor pressure of water is 17 torr. So the pressure of water equals 17 torr. All right. The partial pressure of the gas collected. All right, so we're collecting this gas in here, and it, fills it up a certain amount there. This is a very simple question, and it has to do with Dalton's law of partial pressures. So we've got two gases in here. One is water vapor, and one is whatever our gas is. So what did Dalton say? Dalton said that the arithmetic sum of this value and that value equals the total. So the pressure of this gas plus the pressure of water equals 758 torr. That means the pressure of the gas equals 758 minus 17. 741 torr. All right. Number 18. A flexible weather balloon contains helium gas at a volume of 855 liters. Initially, the balloon is at sea level, where the temperature is 25 degrees and the barometric pressure is 0.947 atmospheres. The balloon then rises. I think what we've got here is a before and after situation. The balloon rises to an altitude of 5,500 feet, where the pressure is 0.785 atmospheres, and the temperature is 15 degrees. What's the change in volume of the balloon as it ascends from sea level to 5,500 feet? Okay, so in order to get all this straight, we need to organize the information in a way that we can understand. What's the initial pressure, volume, temperature? The number of moles doesn't change, right? That balloon is sealed, so we don't have to deal with moles. So initial here, and then it's going to get a certain pressure when it reaches altitude. It's going to have a certain volume, and the temperature is going to be different. Okay, what's the initial pressure? 0.947. The initial volume, 855 liters. Initial temperature is 25, I believe. Yes. Now that's degree C. So we need to add 273 to that one. Okay. What's the pressure at altitude? 0.785. atmospheres. Volume is the question. And the temperature is now 15. Okay. So what relationship do we have here? We have the combined gas equation. So PI VI over NI TI equals PF VF over NF TF. Remember I said the number of moles didn't change. So we can remove that one. It's exactly the same. It will cancel out. We're solving for the final volume. So let's do a little algebra here. So this is going to be in the numerator. We have PI, VI, and TF. In the denominator, we have TI and then PF. Right? So this one moves over here, that one moves over here, and we have this one left. So now all we have to do is insert the values, and I'm going to leave the units out because there's not a whole lot of room here. So the initial pressure is 0.947 atmospheres. Volume is 855 liters. I said I wasn't going to do that. And the temperature final is 288. Okay. The initial temperature is 298. And the final pressure is 0.785. So now it's just crunching numbers. Yes. 997. Liters. Okay. Well, scientific notation, 9.97 times 10 squared liters. All right. Okay, what happened? Okay. Oh, what's the question? Question is not what the final volume is. What's the change in volume? So what's our initial volume? The initial volume is 855. 8.85 times 10 to the second. That's 1.12 times 10 squared. There you go. That's the change in volume. Why did I get 1.12 and 1.42? 997, 855. Well, it looks right. What's the change in volume of the balloon as it ascends from sea level to 5,500? All right. Oh, that was pretty dumb. There. Transposition error. Okay. So now it should be 1.42 times 10 second liters. And 21. consider the unbalanced equation. Looks like we're burning ethanol. We've given a certain amount of ethanol, oxygen. What's the total volume of gas present in liters after the reaction is complete? Assuming the reaction takes place at 1 atmosphere and 25 degrees. Okay, so this is similar to the peroxide equation. We need to balance the equation first. C2H5OH, which they're given as a gas, and then O2 as a gas yields carbon dioxide and water. And we're making this one a liquid. Okay, let's balance the equation. I'm going to go ahead and use the budget method so you can see, so we don't make any mistakes. I could probably do it without that, but let's do carbon, hydrogen, oxygen. So we have 2 carbons, we have 5, 6 hydrogens, and we have 3 oxygens. Over here we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. We're going to keep the oxygen till last. It looks balanced now, but it won't be in a minute. Let's go to carbons first. 2. So that makes 4, 5 oxygen. Okay, now let's go to hydrogen. So we have 2 versus 6. Okay, if we put a 3 here, right, that makes 6 hydrogens. It also makes 3 plus 4 is 7. 7 oxygens. Okay, how do we get 7 oxygens over here? We've already got 1, so we really only need 6 more. So if I put a 3 here, that's 6 plus 1 is 7. There we go. Now that equation is balanced. All right, now let's go to the conditions. 1.55 grams. 1.55 grams. And oxygen is 10 grams. I'm going to put it down here. 10 grams of oxygen. And 1.55 grams of ethanol. That's my abbreviation for ethanol. All right, when we have absolute amounts of both reactants, one of them is going to be limiting. Well, let's find out how much this produces in I'm going to pick carbon dioxide. Let's take place at 1. Total volume of gas present. All right. So we're saying that this is a gas. That's a gas, and that's a gas. But water's a liquid. So liquid condensed has a negligible volume compared to the other reactants and products. So we can ignore this one. But we do have to consider this gas, that gas, and that gas. All right. So how many moles is this? Okay. Let's see. 2 times 12.01, 6 times 1.01, and 1 oxygen. 24.02 and 6.06 and 16. This is 46.08 grams per mole. Divide that into 1.55, and we get 3.364 times 10 to the minus 2 moles of ethanol. Right? If we convert that to carbon dioxide, this would be ethanol here to cancel, CO2 on the top, which is 2 and 1. So it's just 2 times that. 6.727 times 10 to the minus 2 moles of CO2. Now that's if all of the ethanol is converted to CO2. What if the oxygen is converted to CO2? Well, we need to know how many moles first. Mole, and this is 32 for oxygen. This is 3.125 times 10 to the minus 1 moles of oxygen. And we convert that to CO2. This is 2, and that's 3. So 2 times 3 divide. This is equal to 2.083 times 10 to the minus 1 moles of CO2. Okay, now we know which one's limiting. This is a smaller amount. So ethanol is limiting. And this is excess. Okay? All right. Total volume. Okay. We know all of this is going to be consumed. There's nothing left. So it produces this many moles of CO2, right? We don't have to worry about the water because it's not a gas. This is the number of moles, actually the number of moles of oxygen we start with here. How many moles of oxygen are consumed? We need to convert this into that. So 6.727 times 10 to the minus 2 moles. Actually, that's not right. It's 3.364 times 10 to the minus 2 moles of ethanol. We want to convert that into oxygen. Excuse me. So it's 3 times that value. This is 1.009 times 10 to the minus 1 moles of oxygen consumed. Right? If we start off with this many moles of oxygen, 3.125 times 10 to the minus 1 moles of oxygen minus 1.009 times 10 to the minus 1 moles of oxygen consumed. That will tell us how much oxygen is left over. This is 2.116 times 10 to the minus 1 moles of oxygen remain. Okay? That's how much oxygen remains. That's all consumed. And we end up with this many moles of CO2. So the total moles of gas left afterwards. Well, if this is going to be we can approach this problem 2 different ways. We can do a before and after, or we can do the ideal gas equation, right? Because we have temperature, we can calculate the number of moles remaining, we have the pressure, we can calculate the volume. I think this would be the more efficient way to go. All right. How many moles are left after the reaction? Well, we have this much oxygen left over because it's excess, and we have this many moles of CO2 produced. So we have the number of moles is, let's just add these together, plus 6.727 times 10 to the minus 2 moles of CO2, right? That's 2.789 times 10 to the minus 1. So this is the number of moles of gas. 789 times 10 to the minus 1. Then 0.08206. And then temperature is 25 plus 273 divided by, what's the pressure? One atmosphere. Okay. So multiply that value times 0.08206 and 298. And this is 6.82 liters. All right, that was a lot of work. I'll admit, that was a lot of work to get that answer. We have to go through it step by step. You can't just do all this in your head. You got to have the procedures in your head and then follow the procedures step by step. Attention to detail will keep you out of trouble. I know, because I get in trouble all the time. Miss a detail. Well, let's see. I need a fresh marker. 23. Okay. You're playing with a helium balloon on a typical warm California day. Okay, well, whatever. Suddenly, the Celsius temperature doubles. Which of the following is true? Okay, we're talking about temperature change, volume, and pressure, right? So the balloon has the same number of moles in it it always had. So we're talking about a before and after. Initial PV over T equals PF over T. Yeah. All right. The temperature doubles. The Celsius temperature doubles. Degrees Celsius initial times 2 equals Celsius final. Okay, so we've doubled the Celsius temperature, but does that double the Kelvin temperature? This will be 2 times degrees C plus 273. Right? The Kelvin temperature, the Kelvin initial is not the final temperature, excuse me, the final Kelvin is not 2 times, because we added this 273 in here. It's not double temperature. So the actual temperatures are not necessarily needed, but we do have to consider Kelvin versus Celsius. The volume of the balloon will slightly increase. Yes, we increase the temperature. According to Charles, the volume will increase. So B is, let's see, A is false. B is true. How about C? The pressure inside the balloon will double. Well, the balloon's going to expand against the same pressure as before. So the pressures inside the balloon will be the same before and after. Now, during the process, the pressure changes, but when it settles down, when it reaches equilibrium, the pressure is going to be the same. The volume of the balloon will decrease. No. Charles says it's going to increase. Volume of the balloon will double? No. It cannot double because the Kelvin temperature did not double. Celsius temperature did. Kelvin temperature did not double. So the only one that's true is B. The balloon will slightly increase in volume. $24. Which of the following statements is true of 19 grams of fluorine at STP? All right, 19 grams of fluorine at standard temperature and pressure, which would be 0 degrees C, 1 atmosphere pressure. All right. How many moles do you have? Well, 19 grams is the molar mass for one fluorine, but we got two. We got two fluorine. So this is 1/2 mole of that gas. Right? Okay, we know that. Moles of fluorine. Okay, so what are our choices? First one. It contains the same number of molecules as 1/2 mole of oxygen. That is true. Right. 1/2 mole of oxygen would be the same as that many moles of fluorine. Let's see. E says none of the above, so it has to be false because we found a true one. Exists only in the form of ions? No. C, it occupies a volume of 22.4 liters. Is that true? No, that's for 1 mole of gas. That's the molar volume. For 1/2 mole, it'd only be 11.2 liters. So this one's false also. And then D, it contains 6 times 10 to the 23rd molecules. That's 1 mole. It contains half of that, 3.01 times 10 to the 23rd. So the only true one is A. Take a look at 28. A compressed gas cylinder at 137 atmospheres and 23 degrees is in a room where a fire occurs. The fire raises the temperature of the gas to 475. What's the new pressure in the cylinder? All right. So what do we know? It looks like we have a before and after temperature, and we're looking for an after pressure. So we're talking about pressure and temperature. So is there a law that relates those? Well, not a named law, but combined gas equation can help us here. Okay. The initial over the final, over the initial, final, and final. All right. What doesn't change? The number of moles do not change. All right. What else doesn't change? Well, we assume the cylinder is rigid enough that it's going to retain its volume. All right. So the volume stays the same. The relationship now is between pressure and temperature. Okay. So what's the initial Pressure, 137 atmospheres. What's the initial temperature? 23 degrees. Plus 273 equals 296 K. What's the final pressure? That's the question. What's the final temperature? 475 plus 273, which would be 748 K. Yeah. Okay, now we can solve it for the unknown. PF equals PI TF over TI. So now we can put in our values. 137 atmosphere, TF 748 K divided by TI 296. Okay, that's the thinking part. This is the number crunching part. So I get 346 atmospheres. Or 3.46 times 10 to the second atmospheres. Okay, so what happened to the pressure? Well, the pressure was 37 divided. It's about 2.5 times the pressure of the original. That's a lot. That's a lot of change. I would be very surprised if this cylinder didn't eventually rupture, if you don't get it cooled down very quickly. And you can't use it again because it will be stressed, find little micro cracks here and there. You try to fill it again after the fire, and it will probably explode on you. It needs to be decommissioned, chopped into little bitty pieces of steel, recycled. All right. Let's see. 29. Which of the following statements is true about the kinetic molecular theory? All right. A, B, C, D, and E. Kinetic molecular theory. Remember, the kinetic molecular theory says that postulates. Gases are made of very small particles moving very fast, lots of them. But the space between them is very large compared to their size. And they impact with each other, and they impact with the walls of the container, which produces measurable pressure. So A says pressure is due to the collision of gas particles with the walls of the container. Is that true? Yeah, that was true. Gas particles repel each other but do not attract one another. That's false. According to the theory, these particles do not attract or repel. They just act like billiard balls that bounce off each other. Okay. C, at least 2 of these statements are correct. Well, we don't know about that yet. How about D? The volume of a gas particle is considered to be small, about 0.1 mil. It's small, yes, but we don't know how small. And I think it's a lot smaller than 0.1 mil. So taken all together, D is false. It's only partially correct. E says adding an ideal gas to a closed container will cause an increase in temperature. The kinetic molecular theory says nothing about adding a gas to the container and changing the temperature. It does say something about adding a gas and changing the pressure because it's explaining Avogadro's law. So on its face, E is false. And it's not correct at all. So we really only have one. That was false also. We only have one that's true, explicitly true in the kinetic molecular theory. Number 30. That last one, E was very, very subtle, but it's still false. Number 30. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. Okay, magnesium metal plus hydrochloric acid produces magnesium chloride, which is soluble, plus hydrogen gas. Okay, we'll balance it in just a second. If 3.02 moles of magnesium and 3.02 moles of hydrochloric acid are reacted, how many liters of hydrogen gas are produced at 1 atmosphere and 49 degrees? Okay, so the conditions over here, pressure equals 1 atmosphere and temperature equals 49 degrees C. Let's just go ahead and convert it. So that's 2, 12, 322 K. And we're looking for volume. All right, we have to balance the equation first, and we can do that without the budget, I think. We have 2 chlorines, right? We need 2 chlorines over here, 1 magnesium, 2 chlorines, 2 hydrogens. That's it. We're balanced. We just needed that one value. All right, what else are we given? 3.02 moles. 3.02 moles and 3.02 moles. All right. Look at the ratio, 1 to 2. If all of the magnesium is consumed, how much hydrochloric acid is needed? 6.04, right? Twice as much. So this one is limiting. So we can take this one, 3.02 moles of HCl, and convert it to moles of hydrogen gas. This is 2, that's 1. So this is 1.51 moles of hydrogen. All right. Now that we know the moles, we know the temperature, we know the pressure, we can find the volume. Okay, so the number of moles, 1.51 moles, gas constant, temperature, and pressure. All right, 1.51 over 206, 22 is 39.9 liters. Okay. All right. Next, let's try 34. If temperature and pressure are held constant, volume and number of moles of a gas are. All right. Pressure, volume, moles, temperature. Which are constant in this scenario? Pressure and temperature. Constant, constant. So what's the relationship of volume and moles? According to Avogadro, if you increase the moles, you increase the volume. Right? So they're not independent of each other. They're not inversely proportional, right? Only products of variables equal a constant would be inversely proportional. They're directly proportional as quotients. So that's why D is your correct answer. All right, 37. Perform the following conversion of pressure units. Let's see, 1.177 atmospheres. 1.177 atmosphere. Dimensional analysis. We're headed for torr. Right? Do we have a conversion factor that will give us torr and cancel atmosphere? Yeah. 1 atmosphere is 760 torr. So 760 times 1.177. Is 895 torr. All right, 894.5. Well, let's see. This is an exact number, right? They're correct. 4 significant figures. 894.5. That's the correct answer. How about 43? A sample of argon gas occupies a certain volume at 15 degrees. At what temperature would the volume of the gas be 3 times as big? Assume the pressure is constant. So what relationship are we looking at here? Temperature and volume. That is Charles' law. Right? Pressure is constant. We're looking at volume change. And we're assuming that the number of moles isn't changed. It's confined inside the container. So we're looking at initial volume, initial temperature, final volume, final temperature. All right. So 3 times the volume. So what are we saying there? If the volume increases by 3, what's the relationship between these two? This final volume equals 3 times the initial volume. Okay? So we can substitute in there. Let's see. Yeah, we want the temperature. So if we substitute in this one, 3VI, right? So now we have, and we're looking for temperature. So the initial temperature is 15 plus 273. Right? All right, let's solve for the final temperature. That's what we want. At what temperature would the volume of the gas be 3 times as big? So if we put TF equals, here, VI and VFTI. And VF is actually 3VI. And TI is 288 times 288. And then VI. So the VI's cancel, and 3 times 288 would be the Kelvin temperature. 864 K. And our answer is probably in Celsius. So we need to subtract 273, 591 C. Okay. Now, that's the algebraic way to solve the problem. The other way to solve the problem is we know that volume is going to increase in proportion to the temperature. So if the volume triples, then the temperature would triple. And the triple temperature here is 3 times 288, it's 864. So then we just subtract 273 and we have degree C. That's the logical, the reasoning part of solving this problem rather than the equation part. Either way works. $49. Which of the following will give a graph with a straight line and a y-intercept of 0? Okay. I think this problem is getting at Boyle's law. Remember, Boyle's law says pressure times volume equals a constant. But if we divide through by volume, we get pressure on this side, and we get K divided by volume, or K times 1 over V. That looks like a straight line. Y equals mx plus b. But what's b? B is equal to 0. The y-intercept is 0. That's the origin. So if we plot change in pressure with 1 over v, we get a straight line with a slope. Slope equals K. Okay, so do we have any scenarios here that mimic that? Well, no, it seems I'm barking up the wrong tree because I didn't look at the answers. The answers are comparison of volume and temperature. Okay, so get rid of that one and look at volume and temperature. What's their relationship? Volume and temperature, they're already directly proportional. So if we plot volume and temperature and we rearrange the equation, volume equals K times T, right? T goes over here. Well, there we have a straight line again. This one again is 0. So if we plot temperature against volume, and temperature has to be in K, right? Must be in K. If we do that, then we get a straight line with a y-intercept of 0. Okay. So this would be volume. This would be temperature in Kelvin. Remember, with Kelvin, there's no negative. This does not extend that way. It stops there. So the only place it can stop is here. That's the straight line relationship between volume and temperature. All right. Let's go to 52. Solid carbon dioxide is placed into a Ziploc bag at a certain temperature. Solid carbon dioxide sublimes, turns directly into a gas from the solid at a rate of 0.726 grams per minute. How many gaseous carbon dioxide molecules are present after 4.84 minutes? All right, this is a dimensional analysis problem. There's a lot of fluff. There's a lot of blue smoke in that question. So let's bring things out to what we're given. The amount of time passed is 4.84 minutes. So the change in time, not temperature, time, equals 4.84 minutes. Okay. The rate of sublimation is 0.726 grams per minute. 0.726 grams per minute. That's what we're given. The question is essentially moles. And we can convert moles to numbers of molecules. All right. This is not moles per minute, but we can convert it to moles per minute. If we take this value, and remember, we're going to convert each unit of measure into something else. So we do one at a time. This first one we're going to convert is grams to moles. So what's the molar mass that we're interested in? Carbon dioxide, which would be 12.01 plus 32, 44.01. Right? That takes care of grams. Now we're going to convert minutes. Well, actually, we're going to cancel minutes. 4.84 minutes gives us an absolute value of moles that have been converted in this sublimation process. So if we do this calculation, we'll find out the moles of CO2 that were produced in this process. .984 times 10 to the minus 2 moles. Now we can convert that to molecules. Avogadro's number. And that's 4.81 times 10 to the 22nd molecules of CO2. Okay. So this was purely a dimensional analysis problem. 55. The air in the inner tube of a tire of a racing bike has a pressure of 116.8 psi. Pounds per square inch. Convert that to atmospheres. Okay, you need a conversion factor. And if you look in the useful information, it will be given. So we're converting this to atmosphere. Okay, we need to convert PSI to atmospheres. The relationship is 1 atmosphere, it's 14.69 PSI. which is the four significant figures, 7.951 atmospheres. Okay, I know what happened here. The creator of this problem used 14.7, which would reduce the value to 7.946. So choose the best answer. In this case, it's C. Number 60. You hold two balloons of the same volume. Go. Exactly the same volume. One balloon has 1.05 grams of helium. Mass equals 1.05 grams of helium. And the other balloon contains neon. Okay. What's the mass of neon in the balloon? Okay. We don't know what this one is. We have to assume that pressure and temperature are the same. Oops. Right? Temperature. There we go. So the number of moles should be the same. How many moles of helium do you have? Well, 1.05 grams converted to moles. Helium would be 4.00. So 1.05 divided by 4 is 0.2625 moles of helium, which is equal to 0.2625 moles of neon. Now just convert neon back into grams. Moles, grams. This is a different molar mass. Neon is 20.18. Excuse me, grams, 5.30 grams. Well, the best answer in that selection is 5.29. There must have been a rounding error in there somewhere. All right, 67. Hydrogen balloon is at 25 degrees, 1 atmosphere, and has a volume of 1 liter. How many grams of argon gas must be added to the hydrogen balloon to achieve a volume of 3.78 liters at constant temperature and pressure? Okay. So the temperature is constant and the pressure is constant. That means moles and volume are allowed to change. Okay. So we know that if we increase the number of moles, we increase the volume and vice versa. So what's the initial number of moles and the initial volume and the final moles and the final volume? That's what we're after. So the initial number of moles okay. The initial volume is 1 liter. Okay. and the final volume is 3.78. Okay. So if we set this up in a relationship, we have initial over and final over. Okay. The initial, let's ratio the NI, the initial moles and the final moles. So that gives us initial volume, final volume. So the initial volume is 1, final volume is 3.78. So actually we could flip that and say that the final volume ratio to the initial volume is 3.78 times. Okay. How many grams of argon must be added to the hydrogen balloon to achieve a volume of 3.78 liters? All right. We've got a certain number of moles. This initial moles is moles of hydrogen. This is hydrogen. The final moles is moles of hydrogen plus moles of argon. Yeah, argon. Okay. So the ratio, this final is equal to moles of hydrogen plus moles of argon over moles of hydrogen. And that's 3.78. Okay. So how did we get to this one? Well, if this is equal to a certain amount, then this is going to be the difference. All right, let's approach this. This is getting too complicated. Let's look at it this way. If this is the volume, the initial volume, this volume is due to hydrogen. This volume is due to hydrogen plus argon. So what's the volume of argon? The volume of argon is equal to 3.78 minus 1.00, which is equal to 2.78 liters. That's the volume of argon, right? Uh-oh. Lost the video. Okay, it must have dropped off and come back on. Let's go back to the share screen. There it is. Okay, so now we have a volume of argon. And what else do we have? Well, we have a temperature of 25 degrees. Well, 25 degrees plus 273 equals 298 K. We have 1 atmosphere pressure. So we have pressure, temperature, volume. We can find moles. If we can find the number of moles of argon, we can convert it to mass. So this was, I was barking up the wrong tree with that one. The simpler approach is to use the ideal gas equation. We want N equals PV over RT. Pressure is 1 atmosphere. Volume is 2.78 liters, 0.08206. and temperature is 298. So the number of moles of argon would be 8 would be 4.48 times 10 to the minus 8 mole of argon. And we can convert that. Moles on the bottom, grams on the top. We just need argon is 39.95. Moles cancel. (1.79 times 10 to the minus 6 grams. Okay, I did something wrong. Hold on a second. I know what it is. 2.78, 206, and 298. Yeah, that was a mistake. (1.137 times 10 to the minus 1. And then 39.95 times 4.54 grams. There we go. That was a much simpler procedure. (74) You have a partially filled party balloon with 2 grams of helium gas. You then add 3 grams of hydrogen. Assuming constant temperature and pressure, how many times bigger is the party balloon? Comparing before and after hydrogen gas has been added. Choose the best formula to use to solve this problem. Okay. All right. We need formulas that incorporate those factors: volume, moles, mass, and pressure. Okay. What are we starting with? Partially filled balloon with 2 grams of helium. So the mass of helium equals 2 grams. And 3 grams of hydrogen. The mass of hydrogen equals 3 grams. All right. We're saying that V2 is the final volume. V2 equals final. V1 equals initial. And N1 equals initial total moles. And N2 equals final total. Okay. If we combine, if we know PV equals nRT, and we also know that molar mass equals mass divided by moles. Okay. Then I don't know if this is going to get us where we want to go, because we can solve N equals M divided by molar mass, and then PV equals mass divided by molar mass, RT. That's not going to, I'm looking at the answers, and that's not going to get us anywhere near any of those answers, because we've only got pressure, volume, temperature, and mass incorporated there. If we have, let's look at it this way. Suppose we have a before and after situation. Before is just helium, before is just helium, and after is helium and hydrogen. So before P1V1 over N1T1 equals P2V2 over N2T2. And what doesn't change? Let's see. After pressure doesn't change and temperature doesn't change. So pressure doesn't change and temperature doesn't change. Right? So if we compare, if we have V1 over V2 equals N1 over N2, we would need to know the initial volume, the final volume. Let's see. How many times bigger? So we're comparing the volumes. So this one's going to be bigger than that one. This is going to be bigger than that one. You have to base your answer upon what's given. And what's given has mass in it, but the mass ratios are not going to be correct, right? The ratios, the change in volume is related to the change in moles only, right? Mass is irrelevant. So we need to know initial volume, moles before, moles after, then we can find the final volume. Right? So V2 over V1 equals N2 over N1. Just flip that equation, and that gives you the answer. That's not a very well-written problem, I'll have to admit. But it is true. No doubt about that. Let's see, 78. Which conditions of pressure and temperature are most ideal for a gas? This is just memorizing. A real gas approaches ideal gas at high temperature and low pressure. And the reason for that is derived from the kinetic molecular theory. At low pressure, you have fewer molecules involved. That is, the amount of space available is huge, much larger compared to the space required for the individual particles. So that means that you're going to have less frequent collisions. High temperature means that when they do collide, the kinetic energy of the collision is so great that the attractive or repulsive forces are insignificant, right? We can still treat them as if they're just billiard balls. So A, low pressure, high temperature will give you ideal gas conditions. Now, as a practical matter, what does that mean? What is high temperature and low pressure? Well, 1 atmosphere is low pressure and room temperature is high temperature, right? What compared to what? Compared to 0 K, right? 298 is 25 degrees Celsius. So 298 K is very high K temperature. And 1 atmosphere is very low pressure compared to what? Compared to 100 atmospheres, 200 atmospheres, 300 atmospheres. 79. A gaseous compound containing carbon and hydrogen was analyzed and found to consist of between 80 and 90% carbon by mass. At 145 degrees and 1 atmosphere, the density of this compound is 2.45 grams per liter. What's the molar mass of this compound? All right. If you're asked to determine the molar mass of any compound, go back to the definition. Right? M, or I use a molecular weight, is mass per moles. Okay. This compound contains carbon and hydrogen only, and is found to consist of 80 to 90% carbon by mass. So if it's carbon and hydrogen only, and it's between 80 and 90% carbon, let's just take 85% as an average. So the carbon contribution of this compound, say, is 0.85 of 12.01. What would that be? That would be 10.2 grams per mole. All right. That would mean that the hydrogen would be 15. 1.01. 0.15 times 1.01 would be 0.15. Or we would have like 10.35 grams per mole. Okay. At 145 C in 1 atmosphere, the density of the compound is 2.45 grams per liter. Right. If this is the molar mass, grams on the bottom and liters on the top. Let's see, I may be barking up the wrong tree here. Yeah. Scratch that. I'm going to approach this a different way. I'm going to use, we're given density. Density equals mass per unit volume. Okay. We're given molar mass. Molecular weight equals mass per mole. We're given gas conditions, which is PV equals nRT. Now let's combine these so that we end up with a molar mass answer. So what do we have here? Molecular weight. We can solve this one for mass. So molecular weight equals D times V over N. Okay. Well, we still want to keep this one. And we're given density. Which one do we want to solve for now? Volume or moles? Either one, actually. Actually, let's do moles. Moles equals PV over RT. So now we have dV over PV RT. Denominator comes into the numerator. We have dV RT over PV. V's cancel. So the molecular weight is equal to density times the gas constant times the temperature over pressure. Do we have values for each one of these? That's the question. Density, 2.45 grams per liter. Well, let's see. The gas constant is going to determine what units of measure we can use. So this one is 0.08206 liter atmospheres per mole K. So temperature must be in K, and the temperature is 145. 145 plus 273 is 811, 418. That takes care of K. Density now is going to have liters in it, liters and mass. So 2.45 grams per liter. Right? So liters in the denominator, numerator, that cancels. Okay. How about down here? Pressure. Pressure is what? 1 atmosphere. That cancels. What does that leave us with? That leaves us with grams per mole. That's molar mass. So now all we have to do is say 2.45 times 0.08206 times 418 divided by 1 is molecular weight is 84.0 grams per mole. Okay. It just occurred to me that this is a simpler way. All right. Okay, 81. You got 10 minutes. Let's see. 81. Oh, that's the last one. Good. We got time. So 81. What's the question? 15-gram sample of a hydrocarbon is placed in a balloon at 1 atmosphere and 25 degrees C, and the volume of the balloon is 12.2 liters. Okay. The hydrocarbon is 79.89% carbon and 20.11% hydrogen by mass. Determine the molecular formula of the hydrocarbon. All right. Let's put down what we know. Hydrocarbon. All right. When we say hydrocarbon, we mean carbon and hydrogen only. Just those two. That's a hydrocarbon. So the mass is 15 grams. Mass is 15 grams. Balloon is 1, volume is 1, pressure is 1 atmosphere. Excuse me. Pressure is 1 atmosphere. Temperature is 25 degrees. Degrees C plus 273 equals 298 K, just in case. Volume is 12.2 liters. And the hydrocarbon is 79.89% carbon and 20.11% hydrogen by mass. Okay, this problem is full of blue smoke. Okay, we have two possibilities. We can approach this problem like we have in the past and take the percent mass for each carbon and hydrogen and run through it and calculate the mole ratio. But I think what we're getting at here is to use what we know about the masses, 15-gram sample of hydrocarbon. Okay. So I'm going to try to solve it the way that I think the author of the problem wants it solved. So if we have 15 grams, and the amount of carbon in that is 79.89%. So 0.7989 of that value is the mass of carbon. Which is 1.198 times 10 to the first grams of carbon. And the remaining is 2011. This is 3.0165 grams of hydrogen. Okay. We can determine the mole ratio here because we know the molar mass of carbon. And we know the molar mass of hydrogen is 1.01 and 12.01. Right? So that's, let's see, let's do this one. 1.01 is 2.99 moles of hydrogen in that sample. And then divided by 12.01 is 0.998 mole of carbon. So within experimental error, what we have is an empirical formula of 1 carbon and 3 hydrogens, right? 1 to 3. So we have the empirical formula. All right. This other information would tell us how many moles is that. Okay. So if we use this formula, nRT, N equals PV over RT. I'm going to leave the units out. Pressure is 1. Volume is 12.2. R is 08206. And temperature is 298. This is 0.499 moles of the compound. Okay. So if this is actually how many moles of the compound we have, and this is the actual mass, we can produce the molecular weight of the compound is mass per mole, 0.499. That's going to be close to 30. 30.07. That's the actual molar mass of the compound. Well, what's the empirical weight of the compound? Well, it's 12.01 plus 3.03. 4, 0, 5, 1, 15. So what's the ratio of these two? The ratio is about 2, which means CH3 to the N equals 2. It's C2H6. That's the molar mass of the compound. I mean, that's the molecular formula of the compound. And that's it. Now, if we look at useful information, which is available, let's see, we've got all the formulas over here. We got 1 atmosphere, 14.69 psi. Remember that one. 760 torr for 1 atmosphere. Okay, so you got everything you need right here. Just be sure and make a copy of it before you start the exam. All right. And I think we're almost 11 o'clock. So we're done for the day. And remember, April 10th, there will be no class. I will not Zoom in. I won't be here in person. So just study for the exam next Tuesday. And if you need to get in touch with me, the syllabus has my contact information. So I'll be available. I may not be able to answer your call right away, but I will respond. Okay.